Okay, one nice thing we get out of this is that, well, you can have a power series and take its derivative and you still have a power series. So you can take infinitely many derivatives of a power series. And you also get the usual Taylor formula for the coefficients of a power series right here. This is just obtained by taking derivatives over and over again. So certainly f of z naught in this formula will give me a naught. But then I take f prime and get the derivative. And when you plug in z naught into this, we'll get a1, and then we take another derivative. And before I take another derivative, it's helpful to do a small shift in this formula to avoid potential negative powers. So I'm going to shift this so that I start at 0. And you do that by shifting the coefficients. And this makes it a little easier to move on to the higher derivatives. So what you do is bump up the indices by 1 and throw in a factor of n plus 1. So this is just by pattern following. And now this starts at 0. And then you get the second derivative at z naught. Well, I'd get that by putting in 0 for n. So we'll get 2 times a2. And so far the formula is correct, but you'd have to do this multiple times. And you can get the full formula for, say, the nth derivative if you just keep following the pattern here. And basically what we're doing is you start at n plus m, and you go all the way down to n plus 1. And you get this formula. And what happens when we plug in z naught? Well, we're going to get the 0th term here, which will be m times m minus 1 all the way down to 1 am. So we indeed get the formula m factorial am is equal to the mth derivative at z naught. You can also come up with a formula for this expression using binomial coefficients. I'll leave that as an exercise for you. Okay, this is one nice corollary. You just get the Taylor formula for the coefficients. Another corollary is the existence of antiderivatives of power series. So if I have a power series centered at z naught, then I can just take the term-by-term antiderivatives of these monomials to get this expression, and this will have the same radius of convergence as the original power series, so it'll still converge in this disk because this n plus 1 term won't change the radius of convergence. And throwing a constant in front is not going to change the property that when I take the complex derivative of this power series, I'm going to get little f back. So this is just directly from the fact that we have the term-by-term differentiation formula. And then the last part says every antiderivative of f is of this form, and this is just a fact that we proved earlier, that if I had another antiderivative, then big F minus big G would have a complex derivative identically 0, which would imply that they differ by a constant. So g would have to have the same form, maybe with a different constant in front. And that's just what this proof is here. As you can see, having a power series representation for a function is very powerful, and we're going to give a special name to the functions that have a power series representation around every point. Given an open set and a function on that open set, we declare that we call it analytic if for every z0 inside the open set, there's a disk on which f equals a power series centered at z0. Of course, in some ways, this definition is silly because of the following goal. One of a major goal in the beginning of this course is to prove that analytic functions are the same as holomorphic functions. So the point of this is that checking that something is holomorphic is generally easy. You just have to check existence of complex derivative and the continuity of the complex derivative, and even that condition we're going to get rid of later. And then we're going to get from that power series representations around every point, which implies infinite smoothness and existence of antiderivatives locally and all kinds of other nice things. So it'll take us a little while to prove this equivalence. We just proved that analytic implies holomorphic because we proved that power series are holomorphic. Again, the other direction, holomorphic implies analytic is harder, and you prove it using a version of the Cauchy integral formula, and we're going to do that later. Next, let's look at just a real basic example of showing that a function is analytic. So consider 1 over z. I claim 1 over z is analytic on the complex plane minus 0, and we already know this function is holomorphic on that region just because complex derivative exists for quotients away from bad points. But you can show that this is analytic directly. So you fix a z0, and you need to show that f has a power series representation around z0. So you start with 1 over z, and we have to kind of rearrange it so that we can build some kind of power series centered at z0. So I guess I'll just subtract z0 from z and add it back in and try to build a geometric series out of this somehow. So we do that by factoring the z0 out on the left, and we're left with this expression, which we can expand this as a geometric series as long as the expression here is less than 1. So that's just this condition here, that z minus z0 is less than the modulus of z0. So you get this geometric series representation, which is a power series centered at z0. So we get that 1 over z is in fact analytic at every point except for 0. Okay, and one thing we get out of this is that on this disk of convergence, 1 over z has an antiderivative, which we can just compute by taking term by term antiderivatives. And we'll see later that this is a complex logarithm, but for now I'm just going to point out that here's the formula for it. So we take term by term antiderivatives and get this. I brought one of the z0s back in to the formula to make it look a little nicer. Let me show you that. So here was the power series in question, and we had a z0 out here and a z0 to the n right there. So we have it to the n plus 1, and we added 1 to the exponent and divided by n plus 1. And this can be converted back into a formula like this. And this is the familiar power series for log that you might learn in calculus, and we're going to show that it is a logarithm.